Next 20, shift to question 7. A radioactive dye of 4 grams is injected into the bloodstream of a patient. The half-life of the dye is 6 hours. At the same time, the dye is filtered and removed by the body with half-life of 12 hours. 1 gram of the radioactive dye will be found in the blood after 8 hours, 9 hours, 6 hours and 12 hours. Okay? So we have that dye and its initial mass, let's call it m0, is 4 grams. It is injected into the bloodstream of a patient. The half-life of the dye is 6 hours, and at the same time the dye is filtered and removed by the body with a half-life of 12 hours. So please pay attention. This dye is undergoing multiple decay processes. Okay, what are those two processes? One is its own decay, and the other one is the filtering by blood. Okay, now they're saying removed, so that removed basically is equivalent to decay, right? So it is decaying on account of it being radioactive, okay, but at the same time, because it is being removed, it is also a decay process, because decay basically means reduction in the number. Got it? Now in such cases, what is the total decay rate? There are two decays now, so we must have them as dn1 upon dt plus dn2 upon dt, where n1 is due to the own decay and n2 is due to the filtering. Have you understood this part? Yes or no? Total decay. Okay, see, it's not that the nuclei which have decayed naturally, the blood will filter them out again. No. We assume that the radioactive dye, once it loses its radioactivity, once it decays, then it cannot be removed by the body, or even if it does, we don't consider that here. We are considering the radioactive atoms, okay, or nuclei. Fine. Okay. So how will the evolution be? Look here. This is negative lambda 1 n, and this is negative lambda 2 n. Now don't take n1 n2. Okay. Okay, yeah, wait, we need to take that. Minus lambda 1 n1 plus negative lambda 2 n2. Right? Now look, why is taking lambda 1 n1 and lambda 2 n2 wrong? Let's do that. See, the decay process, okay, the decay process is not going to distinguish between an atom which is undergoing decay due to its own radioactivity or due to the action of the blood filtering. So that n1 and n2 distinction or categorization is for our sake, which means n1 here and n2 here will not make any sense. It will be negative lambda 1 n and negative lambda 2 n, because n is the total number of nuclei available at that particular time, which means this will be negative bracket lambda 1 plus lambda 2 into n. Okay, negative lambda 1 plus lambda 2 into n. So total decay rate is basically the addition of the decay rates. Now this will get reflected in the solution also. So n is equal to n naught e raised to negative lambda 1 plus lambda 2 n. T, because the original solution is n is equal to n naught e raised to negative lambda 2. Got it? Now they have not given us the decay constants, but they have given us the half-lives, 6 hours and 12 hours. So can we find out the decay constants? Yes. Half-life is ln2 by lambda. So lambda will be ln2 by half life. We want the blood to contain 1 gram, so n is 1. How much was injected? 4 grams was injected. Okay, 4 grams was injected. Lambda 1 plus lambda 2. Lambda 1 is ln2 by how much? 6. This is how much? Lambda 2 ln2 by 12 t. Correct? Because the second process has half-life of 12 hours. Okay, so we now have 1 upon 4. Now e raised to ln2 is 2, and that with that negative sign it will become 1 upon 2, right? 1 upon 2 raised to what? 1 upon 6 plus 1 upon 12 t. Okay, I hope you got this part. We first took 4 onto LHS, then we took ln2 common. E raised to ln2 is 2, 2 raised to minus 1 is 1 upon 2. Got it? Okay, now let's just compare the powers. Let us just compare the powers. Here it is 2 squared, so 2, and here it is 1 upon 6 plus 1 upon 12 into t. Okay, now this 2 has come because 2 raised to 2 is 4. Okay, now let us simplify. Uh, 12 into 2, 24 upon 3, so that will be 8 hours. Not 8 hours, yeah, 8 hours, 8 hours. Option A. Okay, so when you have multiple decays, the decay constants are to be added.